So, welcome to the first video, Motion on a Variable Force, Chapter 9 of the book. Start off by defining some vectors using vector notation, and you'll notice how we've written it in terms of i's and j's. It just makes it easier to deal with either in vector form column vectors or ij's and k's in two-dimensional or three-dimensional. Okay, so it's quite a logical approach really, and as you can see, the ij and k are just those unit vectors going in those particular directions. In vector terminology, the displacement of vector is given in column or component form. The distance represented in the vector is called the magnitude, and that's the modulus of it, and it's calculated by using Pythagoras' theorem effectively in three dimensions. And obviously we could use the column vectors as well to give the same result. When we talk about the velocity, this time we calculate it by differentiating the displacement vector. So as you see, you take it in component form, differentiate with respect to t each of those individual components. And a nice notation we can use is put a little dot above each of the x, y's and z's, and that just means differentiate with respect to t. So it's just a shorthand way of being able to write the same thing. The magnitude of the velocity is the speed, and that is calculated in the same way as we would have done for the displacement using Pythagoras' theorem. And when we come to acceleration, acceleration can be given in a form as a vector, or it can be given as a magnitude if you ask for the magnitude in it. So, and you see there's got a double dot there, so x double dot meaning differentiate it twice with respect to t, and the magnitude the same way as Pythagoras' theorem in 3D. So here's an example as we're going through is to work out, to using the fact that we know about the vectors and we know we have to differentiate them. So as you see, all I've done to start with is I've differentiated the vector, the displacement vector to get the velocity, and I differentiate it the second time to get the acceleration. And then you notice in the acceleration there's no j component because it's obviously differentiated to 0. Substituting with t equals 2, as you can see that it works out just by just a straightforward substitution into it, work out the ij and k components and working them through. So there we go, I get our position vector at that point. When I want to work out the speed and the magnitude when t equals 2, obviously the magnitude we're now going to work out using Pythagoras' theorem and effectively in 3D and working it through, and we get our answer there, which we can give in exact form or to whatever degree of accuracy we want. And similarly, when we're doing the same thing for the velocity, substituting t equals 2 for the velocity, and that's going to enable us to be able to calculate what the vector at that point would be, and then by using the magnitude of it, that will give us the speed at that point. Okay, and the same scenario as before. You'll notice with regard to the acceleration that the acceleration has got no component of t in it, therefore it is constant. So therefore we just take the two components, just the I and the k components, and we find our magnitude of that. Had there been t's in it, it would have been variable acceleration, because obviously as t would have come into it, it would have changed the speed. So anyway, that's the first example. What we're now going to look at is going to be showing how we can generate the constant acceleration formulas in vector format as well. If we differentiate to go one way, we use integration to go the other way. So a nice little way to remember it, just differentiating going that way, and then obviously going back in the opposite direction is going to be integration. Now that's quite common sense. Now what you must remember is when you're integrating, you must remember the plus c, and an example later on that will show why that is important. Now we're going to show that how we can get the constant acceleration formulae. If we start with the acceleration a and the initial velocity of an object is going to be u, so we know that if v equals the integral of a plus dt, then just integrating it, we're going to find out that v is equal to at plus c. C should be underlined there. Starting conditions allow us to work out what c is going to be, so we now have that v equals at plus u, or more commonly v equals u plus at, but notice this is in vector form. Now to find what the displacement is going to be, we integrate again, but we're integrating the previously found bits in there. So again, same logic, but we're integrating it, so using our usual rules of integration, and don't forget your constant in there. I couldn't R0 this time. R0 is going to be the the initial displacement of the object. I could have used a c in there, to be honest, as well. That would have worked. And you see the similarity between our s equals ut plus half at squared. Now a bit of rearranging, similar to you would have done for the constant acceleration formulae. If we know that v equals u plus at, then we can know what at is going to equal, and we can substitute it into the expression above. Okay, and clearly you can see then, this is just a bit of algebraic manipulation here to enable us to be able to rewrite the displacement formula for us. So here, what I've done here is just using the information above. Okay, and remember to put my constant in there. And then we've got u plus v over 2t, which is another one of our formula used for displacement, which you may well recognise. And then similarly, we can do it a third way. Okay, and this time rearranging it to get to this time to establish what that u is going to be equal v minus at, and similarly substituting that into the original equation and a bit of algebraic manipulation. And you're noticing now we're going to r equal to vt minus a half at squared, as we would have had previously thought. Okay, now a slightly more complicated example here. And this time we're finding what the two forces added together are going to be in vector format, so we can do that. And we're going to use Newton's second law, so F equals ma will enable us to say that there's our vector, there's our force vector, as equal to the mass times acceleration. So very easily getting the acceleration at that point. Okay, now we're going to use one of our constant acceleration formulae. So v equals u plus at, substituting the values that we know in it. So we know the final velocity, we don't know the initial velocity, but we do know the acceleration because we just worked it out, and we know what the time is because we were told that. And then just by multiplying through and then working out that each of the components, you find the initial velocity to be that. Okay, a little bit more challenging the last bit, because here we now know we've got to find out what the velocity is going to be, so we integrate the acceleration, which we'd previously worked out. So we weren't given that, we only noticed a particular point previously. So working it through, we can find out that the initial velocities was the previous result from the part 2 of the question, and then substituting into the expression above, we can find that c is equal to that. Okay, that tells us then that what our actual velocity was at any point in that. We put in our values of c into it, and that's our general formula for velocity. Now we know that the magnitude is obtained by squaring each of those components and adding them all together. And we also know we were given what the velocity initially was, so we were told that it was 10 root 5, so by squaring that gives us 500. Equating those two things together, that enables me to end up with a quadratic expression in t. It just happens to very nicely divide through by 29 quite nicely, ends up with a nice expression which factorizes very easily, and we find that t equals 5. And this ends the session.